Hello, my name is Jung, and today I'm going to be presenting my research designing a novel bamboo-inspired lattice structure for 3D printed total knee arthroplasty implants. Osteoarthritis is a chronic condition where knee cartilage wears down, causing pain, stiffness, and ultimately reducing one's mobility. Luckily, there is a solution for this. Total knee arthroplasty, known as TKA, is a surgical procedure that replaces the damaged joints with titanium implants. Yet, lack of personalization, wear and complications, and frequent repair are all current limitations of TKA. One promising solution is personalizable 3D printed TKA implants. You basically have to create this by stacking these small structures called lattice structures on top of each other. However, because the design space is so vast for these lattice structures, it's almost impossible to test each design one by one, and it also takes a lot of resources and a lot of time. Those were my questions 8 months ago, and I was also wondering, how can we make a more light, more durable, and more biocompatible lattice structure? How can we do it faster and at a lower cost? My solution consists of 2 points. First is a bamboo-inspired design. Second is a FEM and machine learning-based approach. By utilizing these two techniques, I was able to create a lattice structure that is both lightweight, durable, and also enhance osseointegration abilities. I was inspired by the hollow cross-section of the bamboo and the nods of the bamboo. And here is a sample lattice structure. The first method that I used was finite element method simulation. By using these material properties, I was able to simulate how a titanium implant would react under certain strain conditions. Second was a machine learning-based approach. I had a design goal of optimizing normalized energy absorption, which was characterized by energy absorption over packing density. I also used Gaussian process and Bayesian optimization for my approaches. Here are my results. So I generated 20 different lattice structures at the beginning, and I used 16 of them to train and used 4 to test. I obtained the R-square value of 0.8, which was deemed sufficient as a baseline estimator. And then I used Bayesian optimization, and as you can see here, the energy absorption continuously increases until it converges to about 800 megajoules per meter cubed. This is a significant 70.69% increase from previous iterations. Also, the packing density converged. It converged to about 0.48. This is very significant because the porosity of the nearby bone is within zero point 0.4 to zero point 0.6, meaning that the new structure can be more, it exhibits enhanced osseointegration abilities compared to other structures before. Here is a diagram of my optimal lattice structure. And on the right is a validation of my optimized model. I introduced three unseen variables to the machine learning algorithm, and it produced a R-square value of 0.85. This signifies that my algorithm, machine learning-based approach, and my final structure are all really accurate from this data. I also conducted a SHAP analysis. This basically shows which features contributed the most to creating the optimized design. I realized that higher percent D, which means higher diameter, higher nod width, which means thicker nods, and lower height overall, they all contributed to optimizing the normalized energy absorption, which was a design variable. Conclusions and implications. Key conclusions include 70.69% increase in energy absorption within only 50 FEM simulations, and also optimized pore size for osseointegration, as well as SHAP analysis, which revealed all the geometric effects and insights into how creating future lattice designs. Now, how can this translate into a modern world? How can we actually benefit from this? Well, first, we can create a more durable, stress-resistant, and lightweight TKA. Second, we can decrease complications regarding biocompatibility due to its natural durability and causing less debris. Third is lower price point due to its porosity. Because the packing density is so low, we can naturally use less resources to create this implant, making this more affordable to people all across various socioeconomic ranges. Last but not least, by succeeding this optimization within only 50 FEM simulations, I was able to create a way to accelerate lattice structure design by SHAP analysis and these techniques that are not usually used in today's researches. Thank you for listening to our presentation.